Okay, good afternoon. So, any questions on the homework which is due today?
Kind of questions.
Hmm?
So what kind of questions are reasonable?
I don't know.
I guess I have a question on number two.
Okay.
So the keyword I think in number two is energy efficiency.
Remind me, what is the number two
It
question?
says if you run a system as fast as
Oh,
possible,
yeah, okay.
then you have like a sleep
Mhm.
time versus running it as slow as
Mhm.
possible and no sleep time.
Mhm.
Shouldn't that not have any effect on the energy efficiency?
In some case, it may not. Yeah, so, if you recall the discussion we had that if you simply change the frequency,
Right.
then the energy evens out.
Right.
Whereas if you change the frequency and the voltage, then things differ, right? Now, in this particular case, I've given you the equation for as a function of speed, so kind of frequency and voltage are kind of hidden. Um, so do you think this particular equation that I have given, is it for the case that the voltage is being changed or not?
Okay.
Right? I mean, if it was equation for the case that voltage was held constant and only frequency was being changed, then it would have been of the form to the power s to the power 1, right? I mean, because s is like a proxy for frequency, right? Okay. So this is clearly for the case where voltage is also being changed. Okay, and so okay, so yeah. Okay. Any other? Hopefully, so there was a bit of a bad case of English for me in that problem also, which is the term b is always present. So even in the case when the speed is non-zero, basically. Okay. So just go by that equation. Um, the sensor question. So there is one sensor on this processor. Okay. So it's just a trivial exercise in just locating in the data sheet. Okay, this particular board doesn't have built-in sensors. Otherwise, it kind of takes Arduino shields and you kind of plug them in. So there was a question from another student that are we expected to go around looking for those shields, and the answer is no, because there are obviously a huge number of them. So that doesn't make any sense. But the chip does have one sensor. Anyone look at it? No. Okay, cool. Um, any other questions? What about the last problem?
Yeah.
Okay.
Like the more amount of time you put into a problem, the more number of solutions you can find possible.
I mean, look, some of these problems, particularly the iris problem and the last problem, you might also want to just do a little bit of research and see if anyone else has addressed these kind of things. Okay. I mean, the problems are not invented out of nowhere. So, but if you do refer to any paper or anything like that, then cite it. Okay. No extensions. Okay. So just. Okay, so another thing, I mean, we are in that phase where there are a lot of faculty candidates who are being interviewed, and some of the talks are actually very relevant to this course. So you would see those flyers in Engineering 4 and as well as the ECE corner of Bolter Hall. Next Monday, for example, there is a talk on deep IoT. So basically, deep learning on IoT devices is by someone from University of Illinois. So I mean, I've followed his work; it's pretty cool. So I think it'll be a good talk. So check it out. I think there are going to be another 3 or 4 talks in succession, pretty much in the coming weeks. So just something interesting if you want, because this semester, this quarter, we are not having the regular ECE seminar, so this is kind of in lieu of that. Okay, so a shift in gear a little bit now. So we are going to look at other enabling capabilities and services in IoT devices. So thus far, we kind of spent a lot of time on platforms and how do we schedule computation on these things. But an undercurrent here thus far still was time as one of the properties that IoT systems kind of do care about. So this slide set and the next one is going to go into technologies which help provide that notion of time. Of course, there are other physical attributes of interest. Of course, these devices sense. They often need to know their location. They care about power. So I think part of these device thing is that we care about these physical aspects of computing, and time is one of those. So what this slide set is about is clocks, in effect, kind of the underlying hardware, and the next one is going to go into kind of the protocols and all which work on top of that. So the need to know time has obviously been there in systems for a long time. Originally, it was driven by the need to know one's location, and which led to kind of a lot of advancements in precise timing. So timing and location tend to be very closely interlinked. That is, some of the best ways for us to know our location is by measuring distance using some temporal phenomenon. So sort of some centuries ago, when people were trying to navigate, it turns out that latitude can be measured through the stars, but longitude requires knowing time, because stars kind of move east-west, and so where they are in the sky depends upon what time it is, and so you kind of measure that. So the X prize of the day was basically being able to measure longitude so that the ship could localize within 30 nautical miles, and that in turn translated into developing a clock which was precise enough, in particular, which will not drift more than 3 seconds per day. And in today's dollar, it's more than today's X prize, which is $1 million. This is $2 million. But in any case, it was won by some not kind of one of the highbrow scientists and all, but actually someone who was from a lot more modest educational background. But it kind of led to a flourishing of precise timing technologies. Prior to that, kind of humanity was on a much lazier scale of time, so precision timing hadn't received that much attention prior to that. And so kind of this is just a slide, but eventually we ended up with atomic clocks. Okay, now there are a whole bunch of other things. I mean, pendulums are obviously have been around for a while, but now the precise timing happens because of measuring oscillations of some atom, cesium, for example. And so you have atomic clocks, which actually all the way out there. And on electronic devices, time is maintained through crystal oscillators. These are quartz crystal, which when you apply voltage to them, then they oscillate, and then through a series of some electronic sort of supporting circuitry, you extract a precise timing signal from them. Some other clocks which are used in electronic systems are based around essentially having a tuning fork. And in particular, you create a tuning fork using the so-called MEMS technology, so micro electromechanical systems. You kind of make them on the same silicon chips, and the otherwise kind of the concept, again, a moving mass of some form from which you are extracting the timing signal. Nowadays, there are other sources of time. So very crudely, when you need there are two related things associated with when we call as time, right? One is we need a precise frequency source, and that you can indeed, if you're willing to pay, kind of get things like atomic clocks and all. But then the separate thing is you also need to know what time it is, and by that what I mean is time on your device relative to some coordinate system which is broadly agreed. So like for our society as a whole, there is this thing called UTC, Universal Coordinated Time, which is kind of world standard for time. And so in many cases, you would need to translate your local clock to that, but that's not always essential. In many systems, we only care about passage of time. In other systems, we may only care about ordering of events. And finally, in some systems, we may care about at what UTC time did an event happen. Like, for example, you want to whatever unlock the premises gate at 5 p.m. So kind of those are examples where absolute time happened. As networks emerged and as communication emerged, our ability to transmit time or exchange time also emerged. So over networks, we can run time synchronization protocols which take your local clock and then synchronize time with some reference clock, which, for example, may be the clock maintained in UTC. You can also transmit timing information one way also. So like I can keep announcing like, oh, it's 5 p.m. by my clock, it's 5 p.m. 1 second, and I can broadcast that, and the receivers can receive it. All of these things you would see have challenges, right? I mean, if I'm announcing time, like if I'm saying it's 5 p.m. now, so I would do it according to my clock, but by the time the signal reaches you, there's already a delay. So that one-way delay obviously ends up sort of causing issues also. We'll see that clocks have other issues also. Clocks drift over time, and this is not even taking into account things like relativistic effects. What happens in relativity in time? David? If you accelerate, okay, so the time slows down, exactly. So for example, if you clone yourself and send your clone to on a trip to Mars or something like that, you come back, of course you would come back a little bit younger. So there are relativistic effects, and now our ability to time has reached such a stage that you can measure the difference in relativistic effects between a clock on sea level and a clock on whatever, let's say one of the hills in LA, okay, like we're not even simply because higher up you are, the gravity is different, okay. Gravity is an acceleration, and then closer you are to the center of the earth, you are subjected to a higher acceleration, okay. Precise timing matters a lot to sort of for war fighting. So a lot of advances in timing have happened because of military needs. So for example, precision guidance of missiles, precision guidance of anti-missile missiles, all these kind of things depend upon clocks, and as a result, a lot of precision clocking technologies are also export controlled, and also if you kind of attempt to buy it, the first thing they'll ask is, are you a US citizen or not, before they will even sell it to you. For that very reason, these things called chip scale atomic clocks emerged now almost 15 years ago, or their development started then. So they basically put atomic clocks of a kind of a less capable variety, but into essentially a centimeter cube type package, something that you can put on your board, for example. They're pretty pricey. I mean, currently these kind of things sell for like $1,500 or so, so not exactly something you're going to put onto your smartphone and all, but you do find them in like cellular base stations and things like that. And of course, small satellites and things like that would have them. So, so lots of advances in sort of clocking technology itself, which have emerged, and even if so, even though on your device the clocks may be these crystal oscillators and sort of micro electromechanical type things, and maybe in some cases chip scale atomic clocks, but because devices can communicate, so they also benefit from having access to reference clocks, which are of very high quality. Okay, so cellular base stations help synchronize your phone and things like that. So let's talk a little bit about more about these times. So firstly, the variety of ways that we measure time, but sort of the precision timing is done in terms of certain number of oscillations of the cesium atom, and in effect, a lot of other physical parameters are really defined in terms of the second eventually. Okay, so this is one of the truly sort of a physical measure which is not dependent upon an artificial mass or an artificial object of some form. It is we define second to be this. If you kind of think about it a little bit, I mean, the notion of time is kind of like arbitrary in a way, right? I mean, it is an agreement that we give to certain periodic phenomena. In this case, we are calling that precisely that many state transitions at 0 degree Kelvin of a cesium atom is going to be is what we are going to call a second. Clocks have improved obviously quite a bit even during our own sort of past 10-15 years. Sort of, at least in my lifetime, gone from like pendulum clocks to clocks now that routinely advertise themselves as atomic accuracy clocks and all, which basically listen to transmission from a radio station in Colorado and kind of tune to them. Many other measurements, as I said, are actually really defined in terms of it. And finally, the humanities time scale is this thing called UTC, Coordinated Universal Time. What happens is that the way this is kind of like an interesting notion of time. So you might, if you were to ask me what time is it right now in UTC, that's not a question that can be answered very meaningfully, and the reason is that the UTC time is decided at the end of every 24-hour period. So what happens is there are a bunch of clocks, atomic clocks, and at the end of a 24-hour period, they look at how these clocks drifted the past 24 hours, they average them, and that decides the UTC as it was for the previous 24 hours. Okay, so so if we were to say what time it is with UTC right now, it is really an estimate because the precise UTC time would only be known at the end of that 24-hour period. So it's a weighted average of a bunch of atomic clocks, and you know that weighted average only at the end.
So let's say at the end of the day, you could have UTC time that the clock the average is 5 seconds.
Well, it won't be 5 seconds. I mean, it would be pretty bad. So they are tiny. What it matters is that if there are some timestamps which needed to be that accurate, then you will have to go back and correct it. Okay, but basically at any given point in time, you can only give an estimate of the UTC according to your current clock. That's really what you can do.
Let's say it were like 5 seconds of the actual time. So like every phone, every clock in the world needs to be like 5 seconds to be honest. You know, 5 seconds.
No, remember, okay. Every device in the world is indirectly retrieving its time through protocols from some reference source. Okay, so if let's say there was a jump in that, okay, let's say something magical happened in universe and the time slowed down, then all of these things will slow down because we're talking to them. Devices or whatever, clocks on your devices do not have any innate notion of UTC. They derive it by talking to some sort of a reference, like for example, there are time servers maintained by many organizations. Like there is a machine called time.ucla.edu, okay, which is UCLA's time server. So if you want a good timing while on the campus network, set your time server to that. I don't know how that one works, but presumably it has either an atomic clock or a GPS to then get a GPS signal. Yeah, they're usually multiple for load balancing purposes, and likewise there is time.apple.com, time.microsoft.com, and I'm pretty sure Google and all these companies would have these things as well. So we'll talk about this later, but so we have UTC, and UTC is adjusted in light of keeping it in sync with human expectations. So there are these leap seconds which are added or subtracted to take into account perturbations in the speed of Earth's motion, basically. Okay, so the thing is, and also to correct for other sort of celestial effects, if you may. Now, coming back to compute systems, I mentioned there are many different ways time gets used, right? I mean, one is simply I want to do something at a particular point in time. So I want to say at 5 p.m. Turn on this actuator. In other cases, I want to measure passage of time. So I might say what was the time between now and a particular another point in the code, how much time elapsed. That doesn't require UTC or anything, it just requires passage of time, except that we want the rate of passage to be the same as the rate of passage in UTC, right? So in that case, it's the passage of time we're describing. And even simpler in many cases is we only care about ordering. So like, for example, imagine a database, and a read request came in and a write request came in, and there's a distributed database, and you want to find out which one came first. You don't care about what time it came in all, but you are trying to get the ordering right. Or for example, let's say 2 cameras in my network reported seeing a person. Was that person leaving my home or entering my home? Well, it depends upon the order. I don't really care so much about the precise time in that particular case. Okay, so a lot of studies around time have focused on these different notions of time. So logical time is something which has been very well studied in distributed computing, because when you are doing distributed computation, then the order in which the events happen often take a very important role. The database example was just one, but there are many other examples where sequencing things matter, but not necessarily how they're embedded in a physical time coordinate. So logical clocks, there was actually this whole field was started in 80s, and there's a gentleman called Leslie Lamport who published some of the seminal papers, to the extent that he won Turing Award for that piece of work. So distributed computing has always worried about coordinating things, right? Coordinating things on different computers, sequencing things in the right order, things like that. We earlier in the course we talked about things like semaphores and all, right? Again, imagine there also like who accessed the resource first, these kind of things. This belongs to a broader category of problems called consensus problems. That is, how do different nodes in a network or in a distributed system, how can they agree upon something? Okay, and in this case, you can say very trivially agreeing could be simply about what time it is. So time synchronization in that sense is a consensus problem. That is, we all agree that now is whatever, 5 p.m. So one way of therefore thinking about time is simply it's a number assigned to an event, and that satisfies causality. Okay, so imagine that I have 3 nodes in a system. They are represented by these 3 lines, so P1, P2, P3, and these little red bubbles that you see out there are events in those nodes. Okay, and then within the timeline of a single thing, so like for example in P2, the events are ordered, and that's easy to do. I can always tell locally whether an event happened earlier or after according to my clock at where I am, right? I mean, again, if you go into Einstein's notion of events and all, then the ordering of event depends upon the location of the receiver. But here events are happening at P2, and P2 by just referring to its local clock. So imagine it has a freely running counter, then it and of sufficient resolution, then it can always unambiguously tell which event happened earlier or later. So locally, time stamping an event is kind of straightforward, barring any issues of resolution and rollover of your counter and things like that, but they're all kind of engineering issues. Now, if these were 3 entirely independent nodes, not communicating with each other at all, then unless there was some other way for me to have their clocks be synchronized, I would have no way of relating their timestamps to each other, right? Because they're basically running off their own counters. But if they're exchanging messages, then we get one additional relationship, right? I mean, so if P1 at E11 sends a message which P2 gets at E22, then basic causality suggests that E22 must have happened after E11, right? So the moment systems begin to interact, we begin to get some constraints on across the clocks in these systems. So these arrows are basically, these blue arrows are basically representing causality constraints. And we'll see how one can build up notions of time around that later. Why do we need accurate time? So I kind of gave you some general sense, but some of the examples, locationing. So as I mentioned, our ability to know where we are, the best way we know right now is by measuring distance through some sort of time of flight. So if I want to measure distance between two objects, there are variety of ways one can conceivably go around doing it. One way is simply, can I hear you? And therefore I must be in your range. But that only limits the location to in the range. We can go one step better and we can say, how strongly can I hear you? Okay, so if I can hear you faintly, then I must be far away, and if I can hear you strongly, so it's kind of the receiver signal strength. So I can translate the energy into some notion of a distance. That doesn't work very well because energy propagation is affected by the physics of the environment very badly. So it's a bit of a challenge. So the best one we know is measuring time of flight. One party sends a signal and the other party receives it, and we want to measure how much time it took to travel from A to B. Now, if all nodes in the world, or if both parties were synchronized, then that problem is straightforward. You send me a signal, you timestamp it according to your clock, I receive it, I timestamp it according to my clock, and if our clocks are synchronized, all I have to do is T2 minus T1, and I am good to go. But that's not how, but that presupposes that we have synchronized things. So the alternative in that case is what? How would you measure? If we are not synchronized, how can you measure distance? Use round trip, right? So in that case, you send me a signal and I'll bounce it back, and I'll bounce it back immediately or with a known deterministic delay. And then all you have to do is at your end, you have to measure time of flight between the two, okay? Question for you. I'm pretty sure you guys must have seen these new distant measurement stuff which Home Depot and all sell, kind of the laser units, and you kind of shine a laser, it bounces off, and it gives you millimeter accuracy distance. How do they work? They are not time of flight. Okay, so let's think about it. How long is this room? Maybe 20 feet? Okay. What is speed of light? Huh?
20 nanoseconds to travel.
Right. You will need like a super fancy clock to be able to measure it. It won't be in those $15, $20 devices. So, huh? But what about IR, right? I mean, it's not IR, by the way. It's laser. The reason it's not IR would be sort of diffuse, right? So laser gives you a sharp signal. But what is it that you are measuring to get distance to millimeter accuracy? Huh? No, ultimately everything is voltage, electronic devices. But what does voltage represent, right? I mean, it will be voltage or current eventually, right? But what is it fundamentally? Because, like I said, time of flight is going to be pretty hard. You're going to need a pretty accurate clock. You can do it, but trust me, those devices don't do it. I mean, they will be really, really expensive because they'll need clocks running at tens of gigahertz, and I mean these are pretty cheap devices, right? So what are they doing? Anyone? Huh? Power is not a very good thing. It will be very material dependent and all, right? I mean, so that won't work very well. Yeah, but then it's a function of material, right? I mean, on the other side, but they still work very well.
You can bounce the ball 2 times that, 4 times, or 8 times.
They don't do that because it would be, how would you distinguish the two, right? I mean, it's a very sharp beam, right? Okay, yeah, try to find out how they do it. Okay, okay, but GPS on the other hand does do time of flight. Now the problem in GPS, of course, is that you have a little receiver, there are a bunch of GPS satellites. I cannot bounce the signal back to them, right? The GPS satellite is sending me the signal. GPS satellites have atomic clocks, so they can timestamp it whatever they want, but I cannot do round trip. And I'm not synchronized. I don't have an atomic clock or anything like that, right? So how do you think GPS operate? How do they get the distance? So remember, their goal is to localize you, and they localize you by finding the distance from multiple satellites and then doing some geometry. So how, but if they cannot do round trip, so how are they?
You need to like get more than one signal and like triangulate it.
No, that they are doing, but how are they solving the time problem? How are they getting the distance to begin with? So what they do is the following. They don't simply solve a localization problem. They solve a localization and synchronization problem. So they solve for 4 variables, x, y, z, and t. Okay, and that's why you need 4 satellites in case of GPS to localize you. So the outcome of GPS process is not simply your location, but also the clock on your device is, at least at that point in time when you made the measurement, synced to the atomic clocks which are on the satellites, and those atomic clocks are kept in sync, but that is part of your infrastructure. Okay, so GPS works by solving localization and synchronization together, and so therefore GPS receivers spit out time also, and usually they just send out time over serial port, which is a pretty lousy thing to do because serial ports have a lot of delays. But GPS receivers, the more techie one if you may, they also have a pin called 1 PPS pin, 1 pulse per second, and on that pin there's basically literally they give out a pulse every second, and the main thing is that that pulse is guaranteed to be as accurate, or whatever, almost as accurate as the satellite times. So usually their accuracy is in like order of 10 nanosecond, 20 nanosecond, something in that range. Okay, so so if you take 2 GPS receivers or whatever gazillion GPS receivers and you look at their 1 PPS signal, they would be within a very tight bound of each other. Okay, because they're all synchronizing off that satellite. So GPS is a good way to get time synchronization. But remember, this is every second or so. So in between that 1 second, your local clock is open loop. Okay, so you but conceivably every second you can kind of resynchronize. There is still additional challenge. I mean, keeping. I mean, you may not have visibility to all the satellites. You may be indoors. You may be underwater. Stuff like that. So a lot of places that GPS doesn't work. It's cloudy, rainy, as we have been lately. So all those kind of things obviously create problem. So localization needs accurate time, but they solve the synchronization problem by essentially solving a joint problem, localization and timing. And this generally is something that you would face. Let's say we are trying to very precisely find distance between you and me. Okay, now the challenge out here is that we have to solve collectively 2 problems. So one way, like we said, was if all you cared about location was you could bounce the signal. So I can bounce the signal back and you can measure. But then to measure the distance, I'm actually having to do a round trip. So 2 messages, so I'm occupying more time on the air. And that apart, you are no wiser of around time. So but instead, you can solve a joint timing and locationing problem where we are just sending messages to each other and we are all time stamping it according to our local clocks, and then we take all this data and solve an optimization problem which basically for each one of us finds what's the x, y, z and t. Okay, so you again solve kind of a joint problem. Communication needs timing a lot. So when we saw serial communication, so remember some serial communication send a separate clock, but if you have a single wire over which bits are going, or if I'm wireless, I'm sending you bits, I'm sending it at whatever, let's say 1 megabit per second, but how do you know where to sample it? My 1 megahertz clock may be different than your 1 megahertz clock, because these are physical clocks. Their frequencies are also not identically matched. So knowing the center frequency precisely so that you can sample the incoming bit or symbol precisely is very important, and that's a problem of clock synchronization, or more precisely frequency synchronization, so that frequency and phase synchronization, okay, so that you can sort of sample things in the middle. And if you are poorly synchronized, then the bit error rate goes up. So a lecture or two ago we had talked about that packets had preambles. That was in context of why we cannot just stop the packet transmission in the middle. The purpose of preambles in packets is to synchronize the receiver clock. So preamble is a known bit pattern or a known pattern of symbols. The receiver uses that to train its clock. So essentially during that time the receiver learns, among other things, how its clock is related to the sender's clock. So at that moment in time, the two have now synchronized with each other, so that the rest of the payload of the packet, it can sample it open loop. And the reason we cannot transmit arbitrarily large packets is because as time proceeds, those clocks again drift apart. So after a while, when the receiver thinks it may be sampling it precisely in the middle of the bit, it's not. So communication depends upon very heavily on timing. Other examples, let's say this is called sort of coherent communication. Okay, so kind of basic concept being, let's take this example. Let's say there are two transmitters, both sending a symbol to you. If those two symbols are perfectly aligned in time, then there will not be any collision if they're sending the same thing. Okay, or take the reverse. You are sending a symbol and there are two receivers and they're both listening to it. And if they could combine what they're hearing, then they can have a better shot at detecting what you transmitted than if only one did, because I basically am getting two data. But those two samples have to be synchronized. So if two sensors are making observation about the same thing, in this case two receivers are trying to see what the transmitter is sending, then if they are synchronized, then they can fuse their results to get a better SNR, better signal to noise ratio on detecting what you were sending. So communication and very broadly sensing depend upon time. Sensing also depends on time for obviously the sample rate. Security makes use of time a lot. Can you describe to me some examples where time plays a role in security of a system? So, in what manner? Speak it louder. Random number generator. Not really. I mean, okay, of course they are all digital circuits or some circuit deeply. So yes, there is some notion of time for sure. But I'm looking for something more explicit. Like for example, if system security depends upon a correct notion of time or a correct timestamp or a correct passage of time.
Like sending in like a certain like decoding signal, I guess.
No, okay, I'll offer you one example for sure, right? The digital right management, DRM, right? I mean, some song you are only allowed to play until end of this month. So if the service provider doesn't believe that there is a trustworthy notion of time on your device, then you are going to have a problem, right? So if you could fool the time, so this is a classic case where you cheat a software license by keeping resetting the clock on your PC,
yeah,
right? I mean, okay, so that's, yeah. And of course, that has been taken care of now because these systems maintain more trustworthy time. Okay, there are ways of doing that now. So that's an example. But lot of security protocols also depend upon who did something first or later, right? So the order matters, and therefore time again matters in those cases. Security in many cases depend upon location and therefore depends upon time. So for example, I don't know if any of you have Apple Watches. Any one of you do? Okay, no, okay. I guess we don't pay our grad students that well, but okay, I'm rich enough to have one. But just to give an example, one of the things it does is when I come near my laptop and if I have my watch on and if it knows that it's me who has the watch on, so the watch basically is authenticated. So after I didn't take it off after wearing, so it continually measures, then it unlocks my laptop immediately. Okay, so it's auto unlock of my computers based upon the fact that I, who authenticated my watch and have kept wearing it, have it on me. Okay, so what it is doing is measuring distance. So if I am within a certain short distance, a few tens of centimeters, then it unlocks the device for me, auto unlock. Now it has to measure that distance very precisely, right? It's not sufficient if I'm on that corner. It has to be within a small bubble around it. So it does time of flight ranging, but you're looking at a distance of a foot or 2 or maybe 3 feet, right? You're talking about measuring something which is in nanoseconds, okay? And that indeed is what it does, okay? So it does a time of flight ranging. So that's an example of security. In general, access based on proximity depends upon that. So what if you want to say my car should only open the door if it can verify that the car key is within a certain distance of the car. Okay, so again, time of flight matters. And if you can fool that somehow, if you can fool the notion of distance, so there have been these attacks on cars where people have, like, I'm here teaching my class, and what if you were to put a relay next to me or some adversary near me, and then that adversary's partner near my car, the two relay the signal, and then my car may open. So just a blind radio relay can work, but by measuring time of flight and all, my car can detect that, this key can't be nearby, and therefore will refuse to open. So those kind of attacks happen. Akash.
So if the watch can measure time of flight in such a small space, why can't all those laser pointers measure the same?
This is $600, or the cheapest version is $400. Okay, yeah. So it's not a $20 watch, right? Look, someday, no doubt, these things will filter down, but and those laser things have been around for 10-15 years, right? I mean, so okay, coordinated action, where you have multiple things trying to do something together very precisely. So robots, multiple robot arms operating on a fragile thing on a factory line, okay? So you want to make sure their actions are synchronized very precisely, because even a tiny separation in action can result in a damaged object. Or I'm sure you might have seen these TED Talk videos from UPenn where you have multiple drones playing piano music, okay? They are independently pressing the keys. amazing synchronization if you think about it, right? Now, of course, there you are relaxed more to like millisecond scale or some millisecond scale, but still pretty cool synchronization. And finally, navigation. I already mentioned that with the ships in 1700s and all, but nowadays when you have whatever intercontinental missiles or spaceships and all, I mean, they need to be very precisely navigating. And just think about, like, I mean, US is again embarking upon this shield of anti-missile missile to kind of protect against incoming missiles. So those missiles are moving pretty rapidly, and you have to fire something which kind of hits it. And amazing, I mean, the technology there is all about locationing and timing to make that happen. So lots of use of accurate time in all sorts of systems, even these simple ones, like I was saying, right? I mean, very neat. So how do we measure time? So almost any clock, really, you can think of it as kind of having two parts to it. One is there has to be something which provides the underlying oscillation, kind of the passage of time. Some sort of event which is periodic and equally spaced. This actually, I philosophically have always found this notion of equally spaced a little bit weird, in the sense that there is, if that is our reference of time, then the equally spaced is defined by it. Okay, so what I mean by that is, if I had two clocks, and if clock A is not equally spaced with respect to clock B, then the reverse is also true. So we just happen to pick some source of oscillation as our notion of equally spaced. So we call deep down those cesium atoms oscillations to be the one which are equally spaced, and everything else is really measured relative to that, directly or indirectly, factory calibration, online protocols, and whatnot. So some source, some sort of oscillating device, and the other one is some sort of a counter, which is counting these oscillations. So whether it is pendulum driving the hands of a clock to quartz crystal driving a counter in your computer, they're all essentially kind of doing the same thing. And once you sort of think of your clock in these terms, the next thing which comes up is that how good a time it is. So a term which actually, a project that we started out here some years ago, we kind of began to call it quality of time. Okay, so what is the quality of time? What are the different things that enter into this picture? So going back again out here, quality of time would fundamentally then be a quality of both these things, right? The oscillator and the counter, right? The one which is accumulating things. Both of them can cause issues, right? I mean, so there are many aspects to this this quality aspect. Some of them have to do with the time, some of them has to do with the phase, and some of them have to do with the frequency of the underlying clock. So let's think about it. So one aspect of quality is the quality, the offset in the time. So right, I mean, if you ask me what time it is and I say 6 p.m., then I'm off by whatever, an hour and 10 minutes. So that's an offset. So how accurate? So there are multiple aspects to it. One is to what degree of resolution I can go to, and the other is at any given point in time what the offset is. How stable the frequency is. Okay, so remember again, our notion of stable frequency are those cesium atoms. So let's say somehow I had a magical way of comparing the oscillation of my pendulum or oscillation of my quartz crystal against that reference, then the instantaneous frequency of my local oscillator is going to be in general a time varying function. Okay, sometimes the frequency would be too high than the nominal, sometimes too low. It will depend upon temperature and acceleration and humidity and dust and whatever. So all of those factors sort of come into play. So there are a bunch of different measures that come into play. So one way you can, one aspect is frequency accuracy. That is how well it can realize the defined notion of a second. So what I mean by that is that if I measure time according to my reference, so let's say I had that cesium atomic clock and I measure a second in there, and then I measure what my local clock reported as a second, then the discrepancy between the two is basically going to say something about the frequency error that is occurring. There are some pretty precise clocks in existence, and in fact, some of the work in our department, Professor Behram Jalali, I mean, he does work with things which are in femtosecond kind of level, and I know Professor Aiden's group does work in picoseconds, and also people who are in this optics and these kind of areas, they go into some pretty precise sort of timing, world of timing. Yeah.
So, if I have an atomic clock and I have a clock on my system, how do I measure how by what percent the clock on the board is off?
You have your atomic clock generate events every second. You timestamp those events in your system, right? So you're basically saying my events are coming in from the reference at every second, and I'm going to timestamp it, and I'm going to compare the statistics of these timestamps. If my clock is good, those things, my system would also always report 1 second. Now, the challenge is going to be coming is, remember, I mean, there are bottlenecks of resolution. Your time is being derived from some counter. That counter is being, and your clock has certain minimum frequency. So there are resolution limits and all which come in, but not just that. My clock may be drifting. It may be affected by temperature. So you're going to see a lot of variations in that.
But the process of time stamping itself will require some CPUs and clock cycles, right?
Yeah, but let's imagine that's all hardware, even then. But you're right, we're going to come to that point later, which is by the time you see time in your application, it has already gone through layers of software. So that delay also matters, right? This is equivalent of saying that, remember earlier I was giving that example, if I announce time, right? So if I say 5 p.m., 1 second, it's traveling with speed of sound to you. So by the time you are hearing it, it's already a few milliseconds. Okay, so one-way transfer always suffers from that problem. Okay, we like even something where you have a display and you're looking at it, at least theoretically there is a teeny bit of delay because speed of light does constrain this. But frequency accuracy is different. Frequency accuracy is not worried about that. All it is saying is that my source of oscillation that I am using for my local clock is going to have some variation relative to what the reference is. So that accuracy. When you buy, if you buy, let's say, many of identical quartz crystals, okay, and then you measure them independently, that is what the frequencies are, you're going to see a spread. Okay, that spread is a consequence of variations in manufacturing, is subtle difference in temperature, whatnot. So even identical clocks are not identical, or same thing applies for whatever you buy 10 identical models of the same cuckoo clock. There are going to be some variations in them. Okay, then frequency stability, that's the next thing, which is these things change over time. So if, for example, temperature affects this, then the quartz crystal, then if temperature changes over time, then the frequency is going to change over time, right? So ambient conditions certainly affect things. But besides that, also these devices are fundamentally some sort of electromechanical system, and systems age. The length of a pendulum may change over time. The transistors in my analog circuit may change in characteristics over time, and also just natural degradation / changes in a system over time are going to cause and result in changes in this. Time accuracy, how well a clock agrees with some coordinate system, how well is it aligned with NTP. Oftentimes we don't care about UTC so much as that things be consistent. So like in many applications, it will be sufficient if all the nodes in my home have the identical notion of time. I don't care what it is, but they are in agreement, because then they can do a lot of useful stuff. Whereas in other cases, we may want synchronization all the way up to UTC. And then stability of time, which is the passage of time, like is the same. So let's say, for example, if I were to synchronize two computers right now, and they're both supposed to do something an hour later. An hour later when they do it, will it still happen at the same time or not? Right? Because the clocks, the flow of time in the two may not exactly be the same.
So is jitter a metric for frequency stability?
Yeah, so it is about short term versus long term. Okay, so what Nat is bringing out is like if you look at a digital clock, let's say a 1 megahertz signal, the edges, if you were to compare it against a true 1 megahertz signal, you will see the edges of your real signal are going to be hovering around. There's going to be tiny jitter, and there are a lot of sources of noise and all which kind of result in that. So that's usually what is referred to jitter, but it's basically, you can say it's at a very short time scale phenomenon that is happening. So for example, atomic clocks, when we say that they are the most stable sources that we know of, they're long-term stable, but short-term they're still jittery. Okay, whereas you may have sources which are short-term stable and long-term very jittery. You have a question?
Okay, I have a question about, so frequency stability, is it also including like change in environment, or only including the?
Yeah, the stability of frequency may not be good because of either intrinsic reasons, as in aging of a platform, or voltage stability and things like that, or for external factors like temperature, or in some cases, like if you look at quartz crystal, they're mechanical devices, so they are actually deformed by acceleration. So if you put a quartz crystal on on a turbine which is subjected to a lot of acceleration, then it will deform and it will give heat. You put these things in a different like you take two systems with ordinary clocks, put one of them inside the building with air conditioning so the temperature is stable, and put another one outside where it is subjected to shadow and sunlight and whatnot, you would see the two differ. So yeah, both aspects are important. Okay, so if you think about a clock signal as a periodic signal of some nominal frequency f naught, then any actual instance of that clock will have some deviations from it. Okay, and so at any point in time, the center frequency is the actual frequency of this clock, f of t, is different from f naught, and some of it is this built-in error at the manufacturing time, and some of it is variation at over time that happens. So one sort of term that you would hear is this clock is such a ppm clock, like so many parts per million, or in case of good clocks might be parts per billion. And it's basically this term. It's basically saying nominal frequency minus f of t divided by f naught, and that is saying what the ppm of the clock is. But it's combining these two different terms, right? There is a static error term which is coming from manufacturing errors, and then there is this dynamic term which is happening at runtime, and all of them is being lumped into one. Just to sort of put things in perspective, your ordinary crystal oscillators are probably going to be around 50 to 100 ppm, okay, which basically says that they will make an error of around 50 microsecond every second. Okay, some of it is because of manufacturing effect, and some of it is because of temperature and all those relative effects. Manufacturing stuff you can learn once, carefully calibrate, and then say it is fixed. But then there is all this other spread which is happening because of temperature and stuff like that. And for that, you have to do something at runtime. So you could either design special circuitry which make the clock more stable to, let's say, temperature. So those are called temperature compensated clocks. With those, you can get to 1 ppm, maybe 0.1 ppm. Okay, so you gain significant improvements. Go back to your circuit classes. What's the cheapest way of getting an oscillator circuit?
Resistor and capacitor.
Yeah, RC circuits, right? You kind of create some sort of on-chip, okay, ring oscillator. Anyone knows what that is? Like odd number of inverters in a feedback loop, right? They're all pretty lousy because the delay through these things and the so RC circuits, RLC circuits, the problem is we don't know how to make those passive devices very accurately, particularly on chip. And likewise, these ring oscillators and all, they again, the delay through an inverter is highly variable, highly temperature dependent and all. So again, very hard to get it right. The ppm there might be 50,000, 100,000 ppm. So they're pretty lousy, okay? So timing in a system then really kind of boils down to creating some sort of a hierarchy. You may have a low power, lousy clock, which is disciplined by a higher power, higher quality clock, and then maybe you may have a remote network reference, which is really high quality but hard to get to. Okay. So when you discipline a clock, when you train a clock, you're really doing two things. You are helping it correct for frequency error, and you're also synchronizing time. There are two different things which are happening simultaneously. So frequency errors change in time, and therefore the clock drifts. So if I were to synchronize at the startup of the system, and then I let it run, then it will again deviate because of this ft term, right? It's kind of meandering around and all. There are short-term changes which happen because of environment, and long-term changes which happen because of aging and phenomena like that. And oftentimes this noise, this change in frequency and all, these are presented in the frequency domain. So kind of again to distinguish between short-term phenomenon and long-term phenomenon that are happening. So kind of these two different effects that are kicking in. We talked about jitter earlier. So jitter is very short time variation which is happening. So for example, if I look at a digital clock, kind of the type we find in our system, you would see that the edges of that clock are slightly away from what the nominal according to our agreed upon notion of time, let's say ultimately that sees in clocks. So the edge should have been here where the black line is, but the actual edges might have a spread around it. Now, those of you who are into analog systems and all, you might also often see that people who do A to D converters and all worry about clock jitter. Why do you think they do that?
Sample consistently at the stable clock.
Right. So basically, the sampling is being done at the clock edge. If there is jitter, then I'm sampling the signal at a wrong place. And if you think of the signal as something time varying, so if I'm measuring in a wrong place, so I'm getting a wrong value of the signal. So you can think of that as adding noise, right? So one of the sources of noise in your sensor measurements is the accuracy of your clock. That more jittery it is, okay, the more wrong. And by the way, the same issue will affect communication systems. Communication systems are nothing but sensing systems. They're sensing a radio signal from a cooperating party. So if your clock has jitter, then that will translate into bit error rate, right? So you would see that, like if you get a radio, it will probably say you need to use a clock of this ppm. Okay, if you use something inferior, then your bit error rate will sort of go up. So that's the role of the jitter, and directly translates into error. The other ways this can manifest also. So let's imagine we have a networked system where I have sensors over the space, and they are sampling from sensor data, and they're going to send me the sensor data to a central place, and I'm going to do some fusion and derive something from it. And let's say we are running some time synchronization protocol. So all these things are synchronized, and they are time stamping the signal. So they're time stamping, each sensor is time stamping locally. But no synchronization protocol and all is going to be perfect, so there is always going to be some error in the synchronization. So let's say that synchronization error is some delta. So now if a sensor says, I sampled it at time t1 according to its local clock, even though we are synchronized, my t1 may be delta apart from what he thought, and likewise across the different sensors. So now when I'm fusing the signals from these different places, each one said they sampled at t1, but the t1 itself has a spread because the underlying time coordinate system has a delta spread, and therefore when I fuse them, that will translate into an error. So for example, one very common thing which is done in signal processing is called beamforming, where different sensors look at an arriving signal and then they measure when the signal arrived. Okay, so let's say for example, there were sensors in this front row, okay, and there was an acoustic source out here. It sent out a signal. The waveform will hit the sensor on the leftmost chair first and the rightmost chair the latest. So as the waveform is transmitting, as propagating, these sensors are going to see them at different times. And by combining their readings and together with some geometry, I can figure out that the source was here. Okay, if the source was symmetrically located, then the direction would be different. But now, if they had error in their time, then it will translate into error in where the source was. So timing errors will transmit directly into some error in the inference you are making about what the world. So jitter, clock synchronization error, all of them kind of fall into that category. And finally, in this aspect is the quality of the perceived time. So overall, by the time sort of an application gets to see the time, so to say, that a system has, it's a accumulation of multiple things. Firstly, the timing properties of the clock itself that we talked about, all these drifts and jitters and stuff like that, and the environmental perturbations that are being caused. And finally, perturbation in the signal as it is communicated from the clock to the receiver. And this was a point that I guess one of you were making earlier, which is if you look at our computers, deep down there's an oscillator. It's driving some counter. But when the application asks for time, there's a whole bunch of things which happen in the middle. And so by the time the application gets the return value saying time is X, it's no longer X, firstly, and also you don't even know what's the uncertainty in that process is, because it has gone through this transfer of timing information from that lowest layer to the application, underwent sort of series of things. In between, interrupts may come, stuff like that, all sort of other stuff may happen, scheduling, your application may be kicked out of by the operating system. So all sort of weirdo things may happen in the process. So by the time you get to know the time, it is no longer the time it was, but not just that, you don't even know how off you are, okay? And so all of that kind of in certain applications can kind of matter a lot. So let's do a 5-minute break at this stage before we pick up the story again. Okay, so 5 minutes. Question?
So, at the beginning of class, you were clarifying this. So basically, this term is there throughout the whole process. Like
Yeah, unless the processor is off, then the whole thing disappears. So if it is shut down by powering it off.
okay. Otherwise,
Otherwise, if I'm only running it at speed 0, then processor is on and therefore B is there.
Oh, so but in the question it said that when clock is stopped, then this turns on.
if clock is stopped but the processor is powered up, it's consuming B. Okay, but if the processor is powered off, like we literally shut off the voltage supply to it, then it is 0.
Which we are not doing in the question.
I forgot. You'll have to check the question again.
So I have a question. So I took it more simply because I was like seriously confused because that's one. I'm just looking to be like, okay, well, if we add still provider. So it's just only its own okay, because I heard that we could do is a task 10 and all the subtasks over here, and then all of these tasks would still finish. So therefore, all like is pretty restless. That doesn't matter. All that matters is are we able to do this subtask by its own deadline. So I was just like, well, deadline is 10 milliseconds, then you can perform. I kind of just added.
I'll show you how something about regarding that specifically. I was reading it. Yeah, you don't necessarily have to do that word, but it does make sense yeah, for that microphone, so like when I want to make, you don't necessarily have microphone. And then the file that's right had, which I think I've set that bit when I make so if it's something
So it just gives us all lines and then asks us
Okay, we can resume, I guess. So to summarize kind of the discussion thus far, then there is noise at the lowest level, namely the oscillator, which you can think of as a way, an oscillator is nothing but you can say it's a sensor of passage of time. Then you have errors within this clocking system from a variety of sources, and then finally there are environmental perturbations. So what we see is really a cumulative effect of all of these things that come into play. So this is an experiment by some researchers from Hewlett-Packard, which basically shows what happens in real systems. So what they did was they basically took 3 LCD watches, kind of the cheaper variety that you just like wristwatch kind of stuff, with 100-second readout. So they have displays where they measure to 0.01 second, and they basically had a camera looking at these to capture the time, and the camera was synced to the atomic clock basically. So what you see is 3 clocks which started out at the same point, but over time, and it is in days out here, so it's over a period of around 4 months or so, you see them kind of drifting apart. Then what you do is, so clearly they have some kind of, you see these nice slopes on the left lines, so those are representing some permanent difference in the frequency. So you can say, hey, I can calibrate them and I can subtract them out, right? So I kind of shift them. Then what you see is this curve, where you see a lot of short-term variation. So what it is showing is that not only there was a long-term sort of there was a permanent miscalibration of frequency, which was likely because of manufacturing, but then you are seeing all these variations, which are the effect of noise and environmental factors and stuff like that coming in. Then you can subtract those drifts also, and then you end up with sort of this residual thing which is remaining, and that in effect is the fundamental uncertainty that you are left with, which is you really can't correct for that as well. So the drifts that were happening, I mean, they are still sort of variations, but I can still seek to compensate. I can sort of do some protocol, kind of do some curve fitting and subtract them out, but then there is this rapid variation which is remaining, and that is uncorrectable.
So what's the difference between the second and third chart?
Okay, so in the second one, we are still seeing drifts which are happening over longer time scale, but they still have some patterns. So you can imagine there's a trend line that I can fit to it, and I can learn it through some protocol in case of an actual thing and kind of fit this thing, but that would be some low dimensional thing. And when I subtract it out, there is going to be still some variation remaining, and that's what sort of we are seeing in the third plot. So, so what this is kind of suggesting is that there are things at multiple time scales, things which are manufacturing, which is really a calibration issue. So I can get these clocks, either the factory can do it or I can do it, and so like the manufacturer is selling the clock as F0, but there is some manufacturing thing, and I can just kind of correct for that upfront by comparing it against it. Then there are drifts happening potentially because of environmental conditions, or I guess in their case some other variations, but I can run some protocol which periodically compares the timestamps and all, and then corrects one watch versus some reference, or one watch relative to another. So I can fit a trend line and then subtract that out also, but then there would be something inevitable I would be left with, which is sort of at a time scale that we just don't have the ability to correct. So I guess one way of thinking about it is that the evil, or whatever, the adversary in this case is the spread, not the bias, because bias you can learn and correct for, but the spread kind of comes into play. So another way of saying is, like, for example, another example would be, let's say if I'm sending you timing events, okay, and there's a fixed delay between us, and then there's a spread. The fixed delay you can learn and subtract. the spread you have to live with, and that's the fundamental uncertainty that will exist in these timing systems. So now with this kind of lower level view, let's sort of pop back up and look at a complete embedded system, or for that matter, almost any computer. So there is some resonating element, and actually computers have many, at least two. So there is kind of a clock which maintains time even while your system is off, so that even after your PC has been off for a while, when you turn it on, it still has a notion of time, even at the BIOS level. So there is a real-time clock, which is a very low frequency clock, 32 kilohertz, which maintains kind of the calendar time. And then there is the clock which is in megahertz or tens of megahertz, which is what drives the CPU. By the way, I said the clock is tens of megahertz. That doesn't mean that that's the CPU frequency. So the CPUs work on multiplication of that frequency using phase lock loops, and also CPUs, obviously the core of the CPU may run at whatever nowadays 4 gigahertz or something like that, but you don't transmit 4 gigahertz clocks all over your board because it will like radiate like crazy. So that conversion to higher frequency happens on chip. Okay, so we have some resonating element. There would be some analog circuitry which will extract the periodic signal out of this. So if you monitor this resonating element and you look at it, it will look like a lot of gibberish, but there is a resonating frequency component which you want to extract. So essentially this clock driver, kind of you can think of it, acts like a filter. It extracts the signal which is at the frequencies of interest and then amplifies it, and that's what it supplies as a clock signal. So at some stage you will have some sort of nice digital signal that you are seeing. So there are different terms that you would see: crystal and crystal oscillator. So usually crystals just refer to the crystal which basically have this noisy analog signal which has a resonant component to it, or multiple enharmonics of it. And then oscillator refers to the surrounding crystal plus the surrounding circuitry, the output of it, which is a digital signal that you can use to drive your flip-flops and stuff like that. The thing that happens in most computers is deep down there is a counter, and the clock feeds into that counter, and that counter is freely running. And then rest of the system time is derived from it. So very commonly what it's done is, and that's not shown out here, is that there is going to be a hierarchy out there. So this counter would be set to generate a signal every time it overflows. Okay, so every time it transitions from all ones to all zeros, so it gets a signal, or maybe whenever it hits some other particular count. So that's a lower frequency signal which then interrupts the software, and then the software updates some variable within the operating system, which is now the system's notion of time. And then you correct that. So remember, this is coming from a local clock, so it's not very good. So if your computer is talking to time servers, it is going to learn a bunch of parameters which help convert your local time into, let's say, the UTC time. So you can think of it as a coordinate transformation matrix, which is transforming your local time to the world time, to the UTC time. And then when an application asks for the time, what you report to it is really this corrected time. Okay, so there's all that magic happens, but for so this software that I'm showing out here, you can think of it, this is the lowest level of the software within the operating system in the time stack, if you may, within the OS. And it can read this counter, it can set this counter, stuff like that, but usually this counter you can just think of it as freely running, and this can read it. The reading may happen in response to an interrupt. So you want it to be very precise, right? So instead of just reading it, you basically have it generate an interrupt, and in the interrupt handler, you update the necessary variable. And if you look at sort of the processors we have, they have all sort of other interesting capabilities, like you can there may be a separate register, and every time the counter hits that value, there may be a signal. You can also, there are so-called shadow registers, so you can say whenever I send it a signal, a copy of the current counter value is put into a register. So there are all sort of other stuff that the timing circuitry provides, but in its simplest form, it would look something like this. Now, on the application side, what's happening? Your operating system will give you some API to access time-related services. So like, for example, in Unix, there is a call called get time of day. Okay. Now, get time of day deep down could be implemented in a variety of ways, but let's say one way could be a system call that allows, remember that variable that I was talking about where the operating system's notion of time is being maintained, that's residing in kernel's memory. You probably don't want to give applications direct access to it, because if they do, then they can maybe snoop into other kernel data also. Now there are ways around this, but therefore you might want to go through a system call. So the application, when it is coming, it will have other additional layers of going through the OS to get access to the information out here. So other issues that sort of come into play out here is that your notion of time is really dependent upon the granularity of that clock. So if, right, I mean, you can't measure time with any final resolution. You also have to worry about things like overflow and all. So again, the overflow, this counter is probably going to be maybe, let's say, 64-bit or something like that. When it overflows, or if it's 32-bit, if it overflows, then sort of a counter with or a variable with more bits is maintained inside the software, and that's where you kind of keep track of these things. This overflow of computer time has bedeviled us quite a bit. I mean, Unix time, for example, those timestamps you see, they are measured relative to some time in 1970s, and they're expected, I think the overflow is going to be in 1938 or something like, sorry, 2038. So there is a point in time where overflows and all happen, and you kind of deal with it. At the end of the day, kind of things that matter to us, there is resolution, which is what's the minimum advancement in time you are able to measure, precision, and then finally accuracy. Okay, all of these things come into play by the time your real notion of time is concerned. So if you look at the lowest level, these counters, I mean, of course, they're going to advance, and then they're going to reset, and they're going to advance again and reset again, and everything else has to be on top, built on top of it by the software. So kind of a similar version to that Hewlett-Packard experiment. So what you see out here is a bunch of embedded devices, and then we pick one of them as a reference, doesn't matter which, so one node as a reference, and then you examine other nodes kind of relative to that. Now, how good your time is in part is going to depend upon how good your resonating element is. And earlier in the lecture, I kind of described loosely kind of a whole bunch of things that are in existence. But if you're making an electronics system, so firstly, a device like your phone probably has maybe a dozen or so clocks for different purposes with different accuracies. And the reason you have so many of them instead of just one is because electronic design is often done modularly. So kind of these different modules with their own separate timing sources. So quite likely each one of the radios in your phone has its own clock. So what are all the radios in your phone? There is GPS, there is Bluetooth, there is Wi-Fi, there is NFC, okay, there is cellular. So right there you have 5 or 6 right there. Then you are going to have clocks for the CPU, and then now that you have multiple processors and stuff like that, so kind of all these other systems. So many clocks residing on these systems. so reducing them, and also because the oscillator, I'm sure you have looked at these crystal oscillators and all, they kind of occupy volume because they deep down are a device. So there has been quite a bit of emphasis on reducing that volume, reducing that space. So that has also driven things towards newer clock technologies. But until very recently, basically the hierarchy looked like this. You had the standard crystal oscillators, quartz crystals, and you could, this is kind of the ppm. So like I said earlier, there's around 50 to 100 ppm. If you were willing to pay, so these things are cents, okay, in cost. If you are willing to pay and you care about the temperature stability, then there are so-called temperature compensated crystal oscillators. And essentially they have circuitry which conceptually are, you can say, measuring the temperature and then compensating for its adverse effects so that the output is stable to temperature. They consume more power because there is additional circuitry, but you get down to single digit ppm, maybe even less than a ppm. Then you can say, hey, I can go one better. Why not seal this clock into a temperature chamber and maintain a stable temperature? Then I can be really nice. So those are called OCXOs, oven control crystal oscillators. Literally, they are kind of in a tiny package. There is a temperature chamber and you maintain a stable temperature. And of course, they consume more power. You can see kind of watt or 100 milliwatts, that kind of thing. But they go down to like 0.1 ppm or so. And then there's a whole bunch of other technologies which I've kind of not listed. But basically, the name of the game is you pay more in power, more in dollars, and you come down out here. Chip scale atomic clocks, I mentioned earlier, which are not shown out here. They are roughly 75 milliwatt or so. They sell for around $1,000 to $1,500, and they're somewhere out here. They're not as good as the big atomic clocks, but they give you ppms of let's see. So they would be, yeah, they would be somewhere around out here. They're better than 0.001. Okay, so kind of up there, and they're not. I mean, they're bigger in size and all, but they're used by military and all quite a bit in portable radios and things like that. Okay, so now I talked about that how sort of these mobile devices and all have been driving technology in a different direction, which is not just accuracy, but accuracy in a volume. So there's a new type of clock which has also emerged, which is something I mentioned earlier, which is that moving mass tuning fork kind of stuff in micro electromechanical systems. And the big advantage is it's done on silicon. So you can put it on the same chip. So now, or at the very least, you can make them, their height can be pretty tiny. So when you put them on a board, they're really very tiny components. And if you are willing to invest in custom chips and all, then you can indeed put them on corner of a chip also. Fundamentally, they are the same thing as your accelerometers and gyros. They're a little moving mass, except in accelerometer and gyro, you pick up the ambient acceleration, whereas here, by applying the voltage, you are making it vibrate and then picking up the time. Apple has apparently started using it. And the way, there was a very interesting episode which has actually happened in late November, which was the following. There was some hospital where they were maintaining some MRI machine, and MRI machines depend upon some liquid nitrogen or hydrogen or something like that. So there was a liquid methane, I forget what it was, but somehow some of it leaked into the HVAC system, okay, of that hospital. And almost all Apple devices stopped working, whereas the Android devices kept working. So what happened was, because since Apple switched to using, because they've been driving the thickness element quite a bit, so they have been using the MEMS clocks. And molecules getting into those moving parts out there at that micro scale essentially clogged the thing. So their clocks died, and therefore the devices froze. So kind of an interesting ramification of technology and the effect it had there. So the thing is, since you're dealing with very small molecules, so standard sealing packaging technologies don't really protect against it, which are really designed for more macro scale particles, if you may. But anyway, so there's a whole choice of things that exist, but the workhorse for most routine electronics are quartz crystal and these new MEMS devices, okay, which have advantages of cost and all, and over time they have basically achieved similar accuracies as quartz crystals. In fact, they have some advantages as well. Professor Sudhakar Pamarti out here, he does a lot of work in that space. So because they are sitting on the silicon chip, so you can surround it with fancy circuitry, so some pretty fancy PLL architectures, and also you can kind of create capabilities that are not easily doable on crystal oscillators, because these are these separate mechanical crystals. Okay, so let's see. So how do we, I'm skipping a few slides. So how do we quantify these clocks? So remember, we saw that the variation itself has a short time scale component and a long time scale component. So when you buy these parts, right, these things, so ppm is one way, but another way is a measure called Allen variance. So it's a statistical measure, but it's used very extensively to characterize clocks, and it's basically defined by kind of the following formula, which is listed out here. What y of n out here is a normalized average frequency over some tau. So you can think of Allen variance as a variance defined over a particular time window. Okay, so over some choice of time period, we define, we get the frequency, and then we compute the expected value of how the frequency is changing from one time instant to another time instant. So n is the sample index in this case. So the main thing out here is by selecting different values of tau, so like a short value of tau will tell you how good a clock is in short time scale, and a large value of tau would mean, so the Allen variance of a clock is specified at different time points. Is there a question?
Yeah, so this might be like a dumb question, but just looking at how variance comes up and whatnot, in software, do any companies or like producers of network applications use like Kalman filters or anything like that to try
Absolutely.
to track their clock?
Absolutely. Yeah, all time synchronization protocols use Kalman filter or things like that to then track the drift of the clock, to track the drift of the clock. So when you think of like NTP, for example, which is a workhorse protocol, it's really complicated under the hood, Kalman filtering and all going on. Huh?
I've been asking
Okay,
people
yeah. So indeed, so you do a combination of tracking and averaging across, or diversity from multiple sources. So that's how you. Okay, so Allen variance is basically gives you stability of the clock at different time scales. So when you look at the data sheets for a clock, or generally any source of time, then Allen variance is how the stability gets characterized, but with a parameter tau, so you can ask for short time scale, long time scale stuff. So for example, if you would say a source of time has an Allen variation of 1.3 10 to the power 9 at a tau equal to 1 second, then it basically says that the instability in frequency between two observations from that clock source, from that time source, would have a RMS value of this 1.3 10 to the power minus 9. So so that's the common measure that gets used. Okay, so yeah, this slide just kind of walks you some example of it. So basically what might happen is, let's say in a system, I may have some reference which is giving me a real time. Okay, I have some hardware, some oscillators driving some counter, and I'm going to take these counter values. Okay, so this is my clock, this is the reference clock, right? If things were perfectly stable, then I should see basically the same jump as I go from 3 to 4, as I go from 6 to 7, and so on and so forth. right? But in reality, that's not going to be the case. There's going to be short scale time scale variations, and there's going to be long time scale variations. So let's say in this chosen scale, we are doing it, so you kind of do subtraction of the neighbors, and you see there are some variations, right? I mean, the last digits kind of change a little bit. Okay, so that's showing you the drift that is happening in the clock, and then you do the averaging, and then you kind of just apply that formula, you get the Allen variation. Okay, so now with that as the measure, we can go back to our various sources of time. So remember, now we have kind of two sources of time in effect, right? I can have a local clock system. I can have things like GPS and NTP and also remote time systems, right? I mean, we can think of Allen variance in context of both of them. So this tries to show that. So what you see out here is, for example, let's try with something. Okay, so let's see NTP. So NTP is a network time synchronization protocol where you basically talk to remote time servers, and then you kind of provide a notion of time. What you see out here is that so if you think in terms of Allen variance, NTP is not very good at short time scales, but it's very stable over long time run, okay, because it is syncing over a network with effectively eventually to some atomic clock, right? So its long-term stability is pretty good, but short-term, because we have all these variations in the network and all, it's not very good. So its Allen variation kind of looks like this. If you look at GPS, again, same story. Short-term, not that great, because again, your measurement noise are going to dominate, but long-term it is very good, even better than NTP, because we have a cleaner cleaner environment. Okay. If we look at rubidium, so it's one of the precision time sources that exists, and what you would see is that over long term, it actually again begins to jitter because it is running open loop. So if I just have some source, then it has some sweet spot where it's stable, but over very long run it is not. So that means even if you have something like a rubidium clock which sell for a few $100 to $1,000, you would need to discipline it using NTP or something like that if you want long-term stability, because long-term it is going to drift away. I think this CTS CBL3B is a temperature compensated PCXO type thing, okay? And I don't know what this is, but point is different sources. The key thing to remember is that we still need discipline via, like you cannot, if you decided that, hey, I'm going to use GPS as my primary timing source, not a great idea. Short term, you have your local clocks are going to do much, these other sources are going to do much better, right? Their characteristics are good. Long term though, you would like it to be disciplined. So ideally, in some senses, your ideal timing system would be an envelope under these, right? I mean, so that when you combine multiple clock sources and have something which is long-term stable, disciplining something which is short-term stable but long-term unstable, and you combine all of these through some algorithms tracking all those kind of things to achieve this goal. And variety of ideas are pursued in this regard, and obviously variety of technologies, and obviously many different sort of cost points. Also, NTP is just the cost of the network. On the other hand, rubidium, like I said, is a few $100, so not very viable in many places. So the lot of choices of these resonating element. I already talked about LC circuits, RC circuits. They are pretty lousy, but they are super dirt cheap. So if you're designing a system, and another advantage of those circuits is they're very quickly up and running. Inverter ring in particular, for example. So if you're designing a processor and all you care about it executes instructions, okay, and you don't really care about what time it is and all, then you can have it up and running with the inverter ring very rapidly. And then later on, your main clock may stabilize and you can switch over to that. So if you're designing systems which have to wake up, rapidly do something, go back to sleep, then just running it off on-chip inverter ring or might perfectly suffice, because what you need there is something which can sequence and can be up and running very rapidly. On the other hand, if you have to wake up and send a radio packet, then you would need a more precise clock, because that more stable clock, because that radio has to communicate. So you would see many chips, including the one on your embeds, for example, usually have this provision that there are multiple clocks, and they will probably have a onboard RC crystal oscillator, RC clock, and you can start with that, and then a little bit later you can switch to your crystal oscillator, by which time it has stabilized, because it takes some time to up and running, and then you kind of switch to that. So so oftentimes you will see these combinations of sources existing. MEMS resonators I already talked about, and then kind of a whole bunch of other stuff. And of course, beyond our electronic circuits, I mean, there are applications where very precise timing is needed. One of the areas where precise timing plays a huge role is particle physics, because they try to measure subatomic particle related events at picosecond, femtosecond scales. So CERN in Switzerland, for example, is a big player in precise timing technologies. And kind of a bit of a hilarious episode from a few years ago, there was this news release that they had observed so-called tachyons. Anyone knows what tachyons are, what those particles are? Okay, so relativity says you cannot go to the speed of light or exceed it. But if particles which are already faster than speed of light exist, then they can be there. So that is perfectly fine. So they are called tachyons, that they start out being at faster than the speed of light. So they reported that some experiments suggested that they had made observations of tachyons, and that would have been a big deal. And then it was retracted because of measurement and timing. Okay, sorry, error in timing measurement. But they drive, so some of the technologies for doing precise timing have come from there. Another driver in recent times actually has been the financial industry, and ability to timestamp financial transactions anywhere on the planet. So that's kind of a lot of money is pouring into the consequence of that also. So resonator technologies are also being therefore pushed. Like I said, MEMS emerged because of the need to have resonating elements which are friendly to mobile devices and stuff like that. Okay, I think I'm almost hitting the end of time here. So, but basically the thing that I wanted to point out is something I had said earlier, that really what happens is that your resonating element, when you apply the voltage, generates noise. But that noise has components at the resonating frequency of the system, as well as at harmonics. And then what happens is your circuitry, you can think of it as really filter plus amplifier. So it basically is a band pass filter, very sharp. So it just extracts that frequency of interest. Sometimes you get the bass frequency, and sometimes you latch onto one of the harmonics. Okay, depending upon which one you do, your frequency would be different. But basically, you extract that signal, you amplify it, and that's what you provide to the outside world. So a lot of the overall performance of the system is therefore is not simply about the original resonating element, but also all of the circuitry that sort of comes into play as well. So I'm going to skip all of that, and yeah, I'll pick up the next time. Next, hopefully I'll finish. I think I'm halfway through the slide set, so next time we'll also get on to sort of the protocols and all which help synchronize things. But as you can see, at least hopefully, the notion of time is quite important, and kind of a lot of interesting things happening on the technology front there. So see you guys on Thursday.